Welcome back, everybody, to a new session on this machine learning course. I just wanted to give you a quick reminder of some of the practicalities and technicalities and where you find the material. So the topic for this week is first a brief repetition from last week, and then we are going to look at the derivation of the equations for ordinary least squares, and that links with the exercises which we put at the end of the lectures from last week. And then we are going to look at discussions of how to prepare data and examples of applications of linear regression. We are going to look at the mathematical interpretation, and that is going to serve as a kind of bridge and stepping stone towards other methods like region lasso regression and the so-called singular value decomposition, which plays a very important role when we are going to invert matrices, as we discussed last week. Now, the reading recommendations for the material this week is something you can find in the chapter 2 on linear algebra in the book of Goodfellow, Benjo and Coville. There is also a set of sections in the textbook by Hasty et al. On elements of statistical learning, where there's a discussion of some of the basic properties of linear regression. Then there is actually a pretty good text on the mathematics for machine learning, which often is not very much detailed in many textbooks on deep learning and machine learning. And this textbook is actually pretty nice. And if you look into chapter 6, there is material which is highly relevant for the exercises which we discussed last week. So if you have time, feel free to look at these exercises, because they will also build up the material for the first project, which we are going to define towards the beginning of November. So this textbook, you have the link here. You can actually look into it. It's a pretty good textbook for a lot of the mathematics which is relevant for machine learning and at the level where we are staying. Now, I wanted quickly to just remind you of the basic GitHub site. And for this site here, where you will find the different videos and lecture materials, you will find the links down here. So the link to the video from last week with subtitles, etc., is something you will find immediately after the lectures. And you will also find the handwritten notes from last week. And the material this week is both covered by the slides, which you can access through this link here. And then you will see later today the video link being uploaded and also the handwritten notes from the lectures today. If you go up a little bit, you will find 2 links. One is to my Jupyter book. And this Jupyter book is not exactly a textbook. It's a kind of intermediate thing between the weekly slides and a kind of textbook. And if you go into that one, you will also see that this is linked to the course which I'm teaching in Norway. And these 2 courses which we are having now will run a little bit in parallel. And you will find some of the same teaching material, which I actually taught in Oslo, but a little bit earlier, because the semester begins 1.5 months before the semester began in the University of Caen. This is where we have the Jupyter book, and also the weekly material, which we will use frequently, and that's the slides which you saw. And it comes in a PDF format. There is a plain HTML. There is a style which I like, which is pretty nice on mobile devices. And then there's a Jupyter notebook, which is the one I will frequently use when I lecture. I'm going to switch between the Jupyter notebook and the handwritten notes. So the material this week is covered by the material you see here, but I wanted quickly to remind you of some of the exercises which we presented last week. And these exercises are exercises which, if you have time, feel free to look at them, and you will find them at the end of the notes here. And if you scroll down, you will find one exercise which deals with the mathematical derivation of the equations for ordinary least squares. And if we scroll down a little bit more, you will find the exercises. So the exercise 1 here There's also something which is covered in the material. And when we calculate the equations for the ordinary least squares, we actually end up with having to take the derivative of an equation like this one. And we are going through some of the details right after these introductory words here. Then there are some numerical exercises just to get you started with using ordinary least squares. And these are exercises which we are going to reuse when we start writing the project. And another topic which we will discuss today is also the splitting of data into test and training. So these are examples which you will also find in the weekly material this week. So if you read through that, you will find hints and tips on how to solve these exercises. Now, feel free to ask questions, unmute yourself, or ask questions in the chat, and I will try to answer them as quickly as possible while we move on. So any questions as far as this concerns the exercises from which we had in the slides from last week? And the material this week is actually going to give you some hints and advices on how to solve these exercises. And we are going to start with the first exercise. And if we now go back to the Jupyter book, so this is the book for this week, the Jupyter notebook, which I also sent to you by email. So after this a brief repetition from last week, we are going to look at the derivation of the equations for ordinary least squares. And then we're also going to look at how to prepare data and look at examples of applications of linear regression. And then we will continue with the material here. And then after the lectures, the video will be uploaded. So let me quickly remind you of some of the basic ingredients which we have and why we typically start with ordinary least squares. You can view ordinary least squares as a kind of low-level machine learning. Now, the learning takes place through a deterministic equation where we have to invert a matrix. So you may ask yourself, where's the machine learning here? But you can think of the learning taking place for a specific algorithm which you implement. The ordinary least squares is a method of choice for fitting a continuous function. Hopefully, it gives us some pedagogical links to other methods like neural networks and support vector machines and other ones. The optimal parameters, or the estimators as they're often called, which we label as beta, they can be obtained through analytical equations. And where the only thing we have to do numerically is actually to perform a matrix inversion and matrix multiplications, and then thereafter we multiply this with a vector. There are analytical expressions for statistical properties, as we will see, like the mean values, variances, and confidence intervals, if you're familiar with these concepts from statistics. We can also derive the same equations from a probabilistic interpretation. So we would start with a distribution for the output y, and based on that one, we can derive the same equations which we started with last week from a linear algebra approach. It's easy to implement concepts like resampling techniques through a popular resampling method, which is called cross-validation. It's easy to analyze something which is called the bias-variance trade-off, which is often used as a kind of tool to analyze whether we are underfitting or overfitting. And you will often see in the machine learning literature something like, how does your model behave compared to the bias-variance trade-off? And this is a typical analysis which is always done. And it links also well with classification problems and logistic regression. And it's also something which allows for an easy understanding of gradient methods. I mentioned last week that at the heart of all of the machine learning methods, which we will cover, and essentially all machine learning, there is an optimization problem. And that optimization problem means that we are going to calculate gradients, derivatives, of the so-called objective function, or what we also label as the cost function, the risk function. There are many, many different names for the same quantity. But that's the quantity which we use to assess the quality of the model and to define the optimal parameters. Now, for methods like Lassonde ridge regression, there is a very nice paper with a lot of the mathematics, which we also cover here in this Wessel van Wieringen's article, which is highly recommended. And similarly, there is a physics reports paper by Mehta et al. And this is an excellent paper because every example which they present in the article, which is a review article of machine learning applied to physics problems, you will find a Jupyter notebook. So you can actually reproduce every single example which they have. Now, what we did last week, just to remind you of some of the things we went through, we made some basic assumptions of the data. And you could think of that as a kind of model already. So one of the assumptions we made is that the data obviously consists of some inputs, which are now set up in terms of a vector. It doesn't need to be a vector. It could be a matrix because we could have many different features. So this could be something like a survey over different patients, and the axis here from x0 up to xn could be something which contains features about the size of a tumor. It could be the radius of a tumor, etc., etc. And then the y's are the so-called outputs, and they could now be represented by a continuous function, which is a typical thing in regression analysis, or it could be a binary output. And if you're going back to this kind of cancer data, you could think of the outputs being representative of a tumor being benign or malignant. Now, the assumption when we deal with linear regression is that the data are represented by a continuous function and some noise. And we assume that this noise is distributed according to a normal distribution with zero mean value and a given variance, which we may not know. So these are the basic assumptions about the data. It doesn't need to be true. So we are assuming that this function f of x is not a stochastic function. It is a well-determined function. And in a certain sense, you could think of that as a good approximation for the input to your data. If you're running an experiment, you may claim that the energy of the beam which you're preparing is well determined, and you know that the energy has this specific value, and then you measure some kind of output y based on that incoming beam energy, just to give an example. So the basic assumption about the data here is that there is a function, an underlying function, which is continuous, and it is a non-stochastic function. So it's seen as a non-random variable. And then there is some stochasticity in the noise here, which we often don't have any idea what may look like. So that means that the y, which we have here, follows this specific function plus some noise. And what we are doing then is that we are going to approximate this function f with some kind of model. So we are going to make a model, which is this y tilde, which then depends linearly on some unknown parameters, beta here. So linear regression comes from the fact that there is a linear dependence in the parameters beta. These are the unknown parameters. And this x here is just a matrix which we define in terms of the data which we have. So one of the measures which we would have then is the mean squared error, which is a pretty common object, which many of you may have seen before. And this is the way we would assess the quality of the model. So in linear regression and ordinary least squares, this is actually the assumption which we make. And we can rewrite this in terms of a vector, because this quantity c of beta, where the beta are the unknown parameters, is a scalar. It's just a number. And that means that if we want this to be a number, then we have to calculate the inner product. So this quantity which you see here, this one, is then translated in terms of the transpose of a vector of the difference between the model and the data set, the output, times the same vector again. And we can rewrite this in a more compact way when we now introduce this matrix X for the model here. You will also see that in many cases, this can be redefined in terms of 1 divided by 2 over n. So that means that when you take the derivative, the factor of 2 disappears. You will also sometimes see it without the factor of 1n, but then it's not the mean squared error, then it's just the squared error. And it's common to divide this by n, because this also forms in statistics, what is called a sample expectation value. So keep in mind now that we don't know the probability distribution, and that means that this quantity here defines a typical sample expectation value. So the thing which we did, if we just scroll down here last time, was actually to take the derivative of this specific function. And this is something which we then can rewrite in a more compact form. And we are going to look at this in the derivations below here. And this is a thing which is relevant for that exercise number 1 from last week. So we can actually rewrite the derivatives here in terms of a vector. And this is given by this design matrix multiplied with this output data minus x times b. And that means that we end up with an expression for the unknown parameters beta in terms of a matrix to be inverted and the same matrix times y here. Now, one of the things which we discuss later today is actually the fact that this matrix which we have to invert may not be a matrix which can be inverted, and that's going to lead us to the singular value decomposition. That's something which will come a little bit later. So if we now move on a little bit, I just wanted to say something about the derivations of the equation which you see here. So how do we arrive from the basic equations here, the derivative of this cost function, and how do we get to this specific value here? So there are some useful properties from matrices and vectors and their derivatives. So we will typically set up a function y in terms of a function f of x. In our case, this is going to be defined by this design matrix times this parameter beta. And just to remind you of some definitions here from basic linear algebra and multivariable analysis. So one quantity which is of interest for us is the Jacobian matrix. And in principle, if now x is a scalar, then this Jacobian is only a single column vector, or what we normally would call an m times 1 matrix. So in our case here, in the general case, it's an m times n matrix. If y is so that means that if x is a scalar, there's only an x0 here. So we can replace all the x0s and xy's, etc., with just 1, and that gives us just a column. Now, if on the other hand, y is a scalar, then the Jacobian becomes a 1 times n matrix. And you can see that because then we don't need y0, y1, y2, etc. There will only be one y, and then we have the derivative with respect to the x's. And in general, however, we are going to have many variables, and that means that we need to pay a little bit attention to the order of things here. So I wanted just to slow down the pace a little bit and just move on to the whiteboard and set up some of these basic equations here. And these are equations which you need in order to calculate the derivative of the so-called cost function or objective function, which in our case is just the mean squared error. So let me just give you some of these mathematical details which we need in order to set up these equations. And I'm going to switch to the whiteboard here now, just to slow down the pace. Now, again, feel free to ask questions if something is unclear. So this is then the material which is related to this first exercise we had. So let's look at this. So this is material for exercise 1 from last week. So suppose now we have a quantity y, which is defined by a matrix A times a vector x. And we assume now that y is given by real variables, and it is a vector of length m. X is a vector which again is given by real inputs, and it has a length n. And then we assume that this matrix is a matrix of dimensionality m times n. So the matrix A is something which we then would simply write out as an A11, A12, up to some A1n. And this goes down all the way to AM1, AM2, and all the way down to AMN. So that's the matrix here. Now, what we are interested in now is to calculate dy of d of x. So when I don't put subscripts, these are vectors. And I'm not going to put boldfaces on it. When I put in the explicit subscripts, that's when I'm looking at these as scalars. But now it's the derivative of a vector with respect to another vector. Now, in order to find the final expression here, it's very convenient to actually write out the vector in terms of the matrix vector multiplication. So we write it out element by element, because then it's very easy to see what the final expression should be, element by element. So these are topics which are sometimes covered in a basic linear algebra and multivariable courses, but often they are omitted. But they are very useful when we are doing machine learning, because one of the main reasons for why we are interested in calculating these type of quantities is that at some point we are going to have to set up derivatives of the cost functions or the objective function. And these derivatives will be given in terms of matrices and vectors. So we would use linear algebra to express our data. And that means that when we want to calculate gradients, we have to find the expressions in terms of derivatives of matrices and vectors. So if I write this out component by component, I have a y of I, a given component, which is then given by a sum over k equal 1 up to n. And then I have the matrix element a I k and multiplied with the vector component x of k. So this is the formal mathematical definition for one of these components. So if I now calculate the derivative of one of these, so I would have a d of y of I, and take the derivative of d of x of j, we know that this one is the same as a d of aij for all i's equal 1 to 2 up to n, m, and for all the j's equal 1 to 2 up to n. Now, that means that what we have now, if we go back to this definition of the Jacobian matrix, so we have the Jacobian, and we wrote this one as a dy of d of x. This is now given by a dy1, dx1. I have a dy1, dx2, and all the way up to dy1 of dx x of n. And this goes down all the way to dym of dx1. And finally, you have a dym of dx of n. So this is a Jacobian matrix. Now, if you now look at the single derivatives, it's pretty easy to extend this to be equal to dy d of x equal to the matrix A. So this is one of the quantities which we will need when we are going to calculate the derivatives in this exercise number 1. Now, we need some more quantities here. So let's now define a matrix as before. So we define y of y equal to a matrix A times x. And A does not depend on x, but x may depend on a vector z. So A, this is assumption we make now, does not depend on X, and X may depend on a new variable, on a vector Z here. So what we're going to show then is that this dy of dz is actually the same as A, the matrix A, times dx times dz. And as I said, when there are no subscripts here, these are all these quantities are vectors. So if we now look at the expression term by term, we have this k equal 1 up to n, and then we have an aik times x of k. If I now calculate the derivative of dy of dzj, so I'm looking at a specific component, this is the same as k equal 1 of n, and then I have my aik, but then I need to take, because a does not depend on z, but I need to take the derivative of x with respect to this component zj. So what we have then, when we look at this is an element, what we might call the element ij of the matrix A times dx times dz. Nothing but that. And then we can easily show that relation here, because that means that when I have that, I get that dy dz is then the same as dy dx, and then dx dz, and that is given by A of dx dz. Now, another thing which is important for us, and as a small digression, let me just bring this up. So we put y is equal to A times x. What we are going to look at is actually the derivative of the model we make, where x is now the design matrix we defined last week. And this parameter beta is the unknown parameter. So we are going to make the connection here with that one, and x is going to be replaced by the unknown parameter beta. So x is normally independent. When we make this assumption for ordinary least squares, we assume that x, this design matrix, does not depend on beta. Oh, sorry, x does not depend on beta. Now, these are some of the kind of small quantities you will need when you're going to find the expression for the derivative of the mean squared error. Another thing which we now define is a scalar. So we define a scalar alpha. And remember now that the cost function which we defined, or the objective function, is also a scalar. It's just a number. When you calculate the mean squared error, that is just a final number. And you want this mean squared error, if you have a perfect model, to be equal to 0. So what comes here is something which is also important for the calculation of the derivative of the cost function. So we're going to assume now that we have this scalar alpha, which is just given by a vector y of t times this matrix A times a vector x. And we are going to assume that A is independent of y and x. And A is again a matrix which has dimensionality m times n. So we make the assumption that y is just a vector now of length m, x is a vector of length n, and A is a matrix of dimension n times n. And we have assumed that's independent of these quantities here. So what we can show then is actually that d alpha with respect to d of y is given by x transpose times A transpose, and that d alpha of d of x is equal to y transpose times A. So the proof goes as follows. So we define a new vector first, define wt, which is equal to y of t times A. So we have assumed that y does not depend on x and A does not depend on x. So that means that we can calculate d alpha, d of x. So y t times A does not depend on x. So that means that when we take the derivative of this quantity, this is simply going to be w times t, and that's given by y of t times A. And you can see that if you just set up the derivatives of the quantities component by component. So alpha is a scalar. So since alpha is a scalar, it means that alpha is equal to its transpose. So alpha is a scalar. That's a basic assumption we make about it. So that means that what I have then is that I can take the expression which I had originally. So I have my alpha is equal to y transpose times A times y times x. Sorry, I have an x here. And that's equal to alpha transpose, which is then the same as x transpose times A of t times y. So that means that when I take the derivative and I redefine a new quantity here, which I can define as a quantity, let's see what would be a good letter here. I can define this as a vector v of t times y. Then v does not depend on y. So that means that d alpha of d of y is the same as x transpose times A transpose. Now, if it is a quadratic matrix, so let's just set up that, and I'm going to give you the result. So if alpha is equal to x transpose times A times x, then if A is a quadratic matrix, which we have to assume now because it's the same vector x on both sides, what we can show then, and I leave that as a small exercise for you, is that this d of x is given by x times A plus A transpose. And the proof is actually easy if you just write out the component by component. So proof, and I leave this as a small exercise, write out component by component. Components. So if we are looking at a specific value of alpha, this is a scalar. This is given by a sum from j equal n. And this is now a quadratic matrix A. So we have the same endpoints n. So this is formally given by aij times xi times x of j. And what you need to do then is actually to rewrite this in component by component and take the derivatives. And then you can actually show that specific expression. So if A, another property here, if A is symmetric, that means that A transpose is equal to A. What you can show then is that this d of alpha, d of x, is equal to 2 times x transpose times A. So these are general relations which are extremely useful for us. Now, when we now come to the calculation of the mean squared error, then we actually need to look at a new type of equation. So for the mean squared error, what we have then is that we have used the mean squared error to define an objective function. It doesn't need to be limited by that. So you can define an objective function which contains the mean squared error plus some additional terms, as we will discuss with Ridge and lasso regression. But you could also let the objective function be defined by the mean squared error. So this is the standard approach in ordinary least squares. So what we have then is just a sum from 1 up to n, and then we have a y of I minus y of I tilde squared. And this y of I tilde is now given by this design matrix, where we now sum over j equal 1 up to p, which are the number of features or the dimensionality of this matrix X. And then we have the components xij multiplied with the unknown parameters beta j, which means that we rewrote this one, the model which we have in terms of a matrix, times this vector beta, where beta now transpose contains parameters from beta 1 up to beta p. So in the nodes, I start with 0 because arrays in Python and C++ start with 0. So you will see the labeling in the nodes starting from beta 0 to beta p minus 1. And X is a matrix, the design matrix, which now is given by some x11, x12 up to x1p. And then I have the data points n to 1, and then x n of p. And it's not element in, but it's equal to. And what we have then is a quantity here, which now has dimensionality n times p. So n is going to be the number of data points. So if you're doing a survey, a medical survey, this n could be the number of patients, and p could be the features of a specific type of tumor. In the applications which we made last week, these p's represented the degree of a polynomial, because we were trying to fit a function, a continuous function. So if we now look at the mean squared error, what we have to calculate then is something which looks like this when we rewrite it in terms of a matrix vector notation. So we have y minus x of beta times t times y minus x multiplied with beta. And what we could do then, when we are setting up these equations, we could define a new vector, which now is given by some quantity omega. So we could label this as a vector omega. So this would be omega t, and this is a vector omega here. So this would again be an inner product. As you can see, we have a vector omega t times omega. So that has to give us a scalar. And then what I would need is then to calculate the derivative of these quantities with respect to the unknown parameter beta. So what I want then is this dc with respect to beta. And I'm also going to need the beta transposed if I want that. And this is the same as d alpha with respect to beta. And it mimics very much of what we saw earlier here. Now, what you're going to see then, when you do the algebra here, is that this d of c with respect to beta, you can show that this is equal to 2 times omega t multiplied with d omega d of x, where x is d omega dx is now a matrix. And we can show that this quantity here is the same as minus, so there should be a n here. This is the same as minus the matrix x. And when I put everything in, this is going to be given by minus 2 divided by n. And then I have y minus x times beta transpose. Sorry, this should be with respect to beta. So this is the matrix x. And this is again multiplied with x here. So I can calculate the transpose of this quantity. And what I would get then, if I do the transpose, so dc d beta t here, and we want this one to be 0. This is going to be equal to -2 divided by n, and then I have my matrix x transpose times y minus x times beta. And this quantity here is now, when we rewrite it, it's going to give us an optimal beta. So this is the best parameter which minimizes the difference between the data, the output, and the model which we have designed. And this hat parameter is the optimal value of beta. And this is given by the inverse of this matrix X times X transpose times X multiplied with the X transpose multiplied with Y. So everything here is known. Now, when we now say that this is an example of machine learning, what we mean is that we have an algorithm in terms of us having to invert a matrix, multiply that with another matrix and multiply it with a vector, and then we learn the value of the parameter beta. So the machine learning takes place through us programming this specific equation. So we learn the optimal parameter beta. And what we would typically do now is to rewrite this beta here as an argument to a minimization problem. Given, the argument is given by these beta values, which have length, are defined by a vector of length p, and then we minimize or maximize this function c of beta. So the exercises, this exercise number 1, which I mentioned, which we put up last week, is something I would like you to go through so that you can derive the same equation as the one you see framed in red here. And I think it's important to have seen this. Now, there's another quantity which we also want you to calculate in that exercise, and that is the second derivative, because that is something we will bring up a little bit later in the next lecture. So if I take the second derivative of this c of beta, and I rewrite it like a d beta, this is a matrix now. This is going to be equal 2 over n of x transpose times x. Now, this quantity in the literature has a name, and it's called the Hessian matrix. So I want you to show that as well. And this matrix is very important because it enters the discussion of gradients when we are going to implement the gradients through Newton's method. Now, there's another thing here which we will show. So let's put this up for later. So one is that x times t, and we will show that after the break, has only positive eigenvalues. Now, the fact that it has only positive eigenvalues means that what we have now is a convex optimization problem. Optimization. The other thing is that this Hessian matrix plays an important role in the optimization when we cannot calculate the gradients analytically like here. So one of the nice things with linear regression is that we have nice expressions for the first derivative and the second derivative. And the fact that we can show that this matrix is positive definite, that is the case when we have only positive eigenvalues larger than 0. So lambda i's are larger than 0. This is a so-called positive definite matrix, which means that if we're looking at this in terms of an optimization problem, and this is the second derivative of the function we want to optimize, then we can actually show that this leads to a convex function with a minimum. And that minimum is going to be a global minimum. It plays also an important role in numerical implementations of gradient searches in what's normally called gradient descent methods. And gradient descent methods are the methods of choice when we are going to optimize a function. And when we come to neural networks, you will see that this matrix here is going to have such a big dimensionality that we have to find approximations to it. And that defines a parameter in machine learning, which is called the learning rate. And we are coming back to that one when we start diving into deep learning methods. But I just wanted to mention this. There's another thing, and this links with statistics. This matrix here is actually the covariance. So x times t times x multiplied with 1 over n is the covariance of the columns of x. So each x has a column, and the column vectors represent the features. And when I want to calculate the covariance, this is actually given by this specific quantity. So there are many, many interesting, nice mathematical links with the standard ordinary least squares. And this is one of the reasons why often ordinary least squares is used as a kind of method of choice to demonstrate many concepts in machine learning and the pertinent data analysis which follows from that. So these were some of the things I want you to look at. And after the break now, we are going to go back to the Jupyter Notebook. And I wanted to mention some technicalities about how we prepare the data and set up the data and how we can run our first implementations of linear regression. So I'm going to pause the recording here. Now, what I want to do now is to give you some examples of how you can write your own code, and alternatively, how you could also use a popular library, which is called scikit-learn, which contains many of the basic pre-deep learning revolution methods. So these are methods like support vector machines, linear regression with lasso, ridge, and ordinary least squares, logistic regression, random forests, decision trees, and many of the other methods which were extremely popular and still are popular, and which were methods which were the most common ones before the deep learning revolution in roughly around 2008, 2009, 2010. Now, what I wanted to quickly remind you now is how to set up a design matrix. So I just wanted to remind you quickly that now what we are going to do is to have some data set, and we are going to define these features or predictors, as you can see here, with there are P of them. And in our case, we are going to try to fit a 4th-order polynomial. So that means that we will have the intercept, we will have the first-order parameter beta 1, beta 2, beta 3, and beta 4. So these parameters are in principle unknown, and we encode them in terms of this so-called design matrix. So let's just quickly go back to the whiteboard and remind ourselves about this design matrix, keeping this expression here in mind. So let's quickly do that, and then we go back to the code here. So what we are having is a model now where we want to define the data set which we have. So we are replacing our function f of x is now being replaced by a model y tilde, which is also a function of x, and we have rewritten this in terms of a matrix x times a beta, and beta is the unknown parameter. Now, in our case, we are making a polynomial fit. So this means that this y tilde, which is the same as y tilde of x of I, these are just the notations which we're going to use, is now given by a polynomial of a certain degree. So we would have a sum over j where we include the intercept, and later we will discuss a little bit how to deal with this intercept. And we move up to p minus 1, where p would then be the degree of the polynomial. So if we have a 4th-order polynomial, then we would have the intercept plus 4 more parameters. And this is now given by some beta j, the unknown parameters, and then we have xi to the power of j, which then translates into the intercept plus the first order parameter times x of I to the power of 1 plus beta 2 of xi to the power of 2 plus till the final point here where we have a beta of p minus 1 multiplied with xi to the power of p minus 1. And this is something which we could, as we discussed last week, frame in terms of a matrix times a vector. And so if, just to remind you of that one, if we look at the vector y tilde transpose, that is now going to contain y0 transpose. And I start with 0 now, since I started the summing over the p's from 0, including the intercept. So I have a given number of model results. And that means that for every entry point here, y0, there is a beta 0 plus a beta 1 times x0 plus a beta 2 times x0 to the power of 2, and all the way up to the final one, which is beta p minus 1 of x0 to the power of p minus 1. And then I have the same with y1 tilde, which gives me a beta 0 plus a beta 1 times x1 plus a beta 2 of x1 squared. And now I'm just leaving out the signs here. And this goes all the way down to yn minus 1. And this is given by a beta 0 plus a beta 1 of xn minus 1 plus a beta 2 of xn minus 1 squared plus. And this is something which we then rewrote in terms of a matrix. And now I'm going to discuss how we actually implement this. So this is something which we then would rewrite in terms of a more compact notation with a vector x, multiply with a matrix x, and multiply with a vector beta. So x is now a matrix of dimensionality n times p. And in this specific case, x is actually given, since we have the intercept here, we have 1. All the way down here, we have x0 to the power of 2, to x0 to the power of p minus 1. We have x1 squared, up to x1 to the power of p minus 1. And then the final result is xn minus 1 to the power of p minus 1. So in general, we would just write this matrix as an x00, x01, up to some x0 p minus 1. And this has an x10, x11, x1 p minus 1. And then we have down all the way to xn minus 1, 0, and xn minus 1 of p minus 1. So this is the more general way of rewriting that. And then we could then define every row here, every column in terms of a vector. So this could be the vector, and when I write it like this, but now with a subscript 1 here, this is now going to be a vector. So I'm trying to make it a little bit bold first. So we can rewrite the design matrix in terms of a given set of column vectors, which in our case translates into p column vectors. So we could rewrite this in terms of a set of vectors, so which we then label as an x. So I'm hoping my bold facing here comes out clearly, that these are vectors. So this is a matrix with p column vectors. Column vectors. Now I'm spending some time on this because this is the way we are going to set up our inputs, irrespective of the method which we are going to use, whether this is linear regression, neural networks, support vector machines, recurrent neural networks, etc., etc. We need to set up our data in one way or the other one. So the number of features, as we've called them, so we have p features or predictors or estimators, etc. So there are many different names depending on the context. And I'm going to simply use features. So the feature now will be the degree of the polynomial. And then we have n data entries. Again, to give you another example, there is a famous data set on credit card debt reliability. So that means that whether you will be able to pay your credit card debt or not. So that is a typical classification problem because it is a yes/no output, whether you pay your debt or not. And this can have lots of features like the age of the credit card holder, the sex of the credit card holder, the type of education, type of employment, etc., etc., etc. So this famous data set contains data set of credit card holders from Taiwan, and I think there's something like 30,000 credit card holders. And the different features are then things like the age of the person, the type of job you have, education, background, married, etc., etc. So these would be examples of the features. And if you have 30,000 credit card holders and you have 20 features, your design matrix will be a matrix of dimensionality 30,000 times 20. And as we mentioned last time, this quantity P is normally much smaller than n. It doesn't need to be. And the usability of these methods depends on the dimensionality of this design matrix. So with this kind of notations which we have introduced and which we also discussed last time, let us now go back to the code and see how we can implement these quantities here when we now make a polynomial fit. Any questions so far? Is everything clear? Okay, so let's go back to the Jupyter Notebook and run through some of these examples, because there are some technicalities which we need to discuss now. So if you now look at the data which I have, I'm going to run this data first without any added noise. And as you see here, this is a second order polynomial. I have the intercept, which is 2, and then I have the term in front of the second order term, which runs like 5 times x squared, and there is no first order term. But now I'm doing something extremely stupid. I'm setting up a fourth order polynomial as my model. So I'm setting up my design matrix. So the first term is just the intercept. And in many applications in machine learning, it's common to leave out the intercept. And we will come back to that. And then I have the first order term, etc., etc. And then I set up my parameters beta. And in this case here, I'm simply inverting the matrix. So I take my design matrix, transpose, multiply with itself, and then I invert it. And then after I've done the inversion here, then I multiply with xt, and then I multiply with a vector y. So this is simply my implementation here. And then I make a prediction, and I'm using all the data to train the model. So we could also now print this value of beta here and just see what kind of values we are getting. So if we run that code, so let's do that, you will see now that I'm getting roughly 0 for all the other numbers. And then I have a 5.0, which is this value, and 2.0, which is the intercept. I can also use the least square functionalities, which I have in NumPy. That's also possible. And then I can now calculate the R2 score, and which ideally should be equal to 1, as we discussed last time. So if I print it, you will see now that this is essentially equal to 1, because I don't have any noise. And then I can calculate the mean squared error, just to assess the quality of the model, and this is 7.22 here. I can also, if I want to, calculate the relative error. So this is us, and this would be the relative error on all the data points, and you see that the relative error is something like 10 to the minus 12 here. Now, what I did here was actually something pretty stupid. So what I could do now is simply to go back and say that I don't want more than a second order polynomial. So I leave out these terms here. And now I rerun everything. And in this case, I'm getting exactly 2.0, 5, and 1.49. I can now recalculate my mean squared error. So remember that in this case, it was 10 to the minus 23. And now you see I get an even smaller mean squared error. And that's simply because, although this is a slightly deceiving model because I have no noise, you see now that the case here now I had 5 orders of magnitude smaller error. And the relative error is also going to be much smaller. You will see now it's 10 to basically 0. 10 to the minus 23 is also basically 0. If I add noise to this, then my results will change because noise is going to give a deviation from a standard second order polynomial. So if I run it now, you will see that suddenly my model here, it doesn't give me exactly 2, it doesn't give me exactly 5, because there's some noise which the model is trying to incorporate in the fitting. So when I'm doing this fit, I'm actually trying now to force these parameters beta to follow closely a function now which also has noise. And you will also now see that the mean squared error is going to be larger than 0. And you see in this case 0.094. So just keep this number in mind. And now we are going to rerun everything here, but now we're going to include a fourth order polynomial. So we include, so let's rerun. And then we try to calculate the mean squared error. You will also see now that when I included the fifth order polynomial, my value for beta 2, which should be close to 5, is suddenly 9.32. So what I'm doing now is I'm adding a more complex model, and I'm trying to fit something which is not necessarily reproduced by a fourth order polynomial. And if I calculate the mean squared error, just keep this number in mind here, 0.094. If I recalculate it now, you will see that my mean squared error is larger. And this is a clear sign that my model may not be the best one. So this playing around with models is something which you will see again and again and again. And I'm just preparing the ground now for the type of analysis which is coming. So this is a simple example for how you can actually solve these exercises. If we now move on, it is pretty common to split the data in terms of train and test. So there is no magic way of deciding whether you should have 20% of the data on test and 80% on training, etc., etc. Now, a word of, caution or warning. In the examples here, we are basically dealing with what we call vanilla examples. So these are trivial cases where we can generate as much data as we want. The normal situation is that the data you have are the data you have. And you could include all the data in the training, and then you could make a model which fits perfectly your data. There's no problem in doing that. However, if you do that, and you apply your model to make predictions on data which were not included in the training, then your model or your prediction may fail totally in reproducing data which was not included. So it's common in the literature to actually split the data in train and test. You would also split it into validation if that's something which is interesting, but often you don't have much data. This is a pretty common situation. Just to give you an example, if you're making a medical survey could span, let's say, 2 or 3 decades, and you would follow something like 100,000 people, and you're surveying things like cardiac diseases and other types of diseases. So if you run this experiment and this survey over, let's say, 20 years, it's very unlikely that you'll be able to rerun it for another 20 years. So the data you would have then are the data you have. And then you need to make this statistical data analysis on that data set. So here we're just repeating the same example, but now with this simple vanilla case, instead of us just regenerating a new data set and using all the 100 points for training, we are now simply splitting this data into 80% train, which you see here. This is this test size. And this is a function which follows the library scikit-learn. And we import it like this from scikit-learn. And this makes the splitting for us. Below here, there is a function which shows you how you can make your own splitting. This does essentially the same thing as the scikit-learn function. The thing which is interesting for us is, however, the fact that this function can be reused with other libraries. So a library like TensorFlow or PyTorch, which was released by Facebook, can easily include this functionality, which you see in scikit-learn. So what we are doing now is simply to perform a training on test data and on the train data. And then we calculate the mean squared error and the R2 score for the training set. And then we apply this on the test data. These are so-called unseen data for the training, which we have performed here. This is a training. And this is my prediction on data which was not included in the training. So ideally, we would like these numbers to be small. So let's see how this runs. And now you can see, again, in this case here, that we are trying to fit this with a fourth-order polynomial, while it is actually just a second-order polynomial. Now, if I do my training now, you see now that sometimes the training MSE can actually be larger than the test. Ideally, it's actually the test MSE which is larger. If I now include just set this to a second-order polynomial, so let's repeat it, and we take away the noise, as we did in the previous example, and we rerun the training. What we would then see is something like this. So both the training mean squared error and the test are just as close to zero as they can be. If I add noise, then the situation will change. It will change also depending on the model which we have. And you see that in this case, for the second-order polynomial, my training set is actually pretty good. And my test is normally a little bit worse than the training. Now, these numbers will change if I add more training points and test points. So if I increase my data set from 100 to 1,000, if I rerun it, you will then see that my test is slightly worse. These things actually change from case to case. But you see now that essentially this is the kind of the image which you may see. Now, the thing I wanted also to discuss with you are topics like for pre-processing your data. And this is done as a kind of default in basically all of machine learning. And there are some things we need to think of when we are comparing our data with libraries like scikit-learn, because scikit-learn does some things by default. So the pre-processing of the data has many different possibilities. So one functionality is called the standard scaling. That means that you center the data. So this should normally not be called scaling, but it should be called centering. So what you're doing then is that you're subtracting the mean squared error from every column in the design matrix. And you may also subtract the mean squared error from the output data. Now, one of the reasons why you do this is that you would like to avoid the importance of outliers. So by subtracting these mean values, the hope is that your data will lie more compact on, if it's a type of first-order polynomial, along a straight line. So it's a way to reduce things like the role of outliers. It also prepares the ground for not using the intercept, because if you look at the intercept column, which you have here, that is just 1. And when you do a linear regression calculation, you can actually recover the intercept through some finite algebraic manipulations. And we will see that a little bit below here. So many of the algorithms which are implemented in libraries like scikit-learns, they often do the training without the intercept. Or they do it with the intercept, but with some caveats. So the pre-processing can span from you scaling the data. So if you set the details, if you're looking at details for health habits, they may include things such as age in the range of 0 to 80 or higher, the caloric intake, and many machine learning methods are maybe sensitive to the scales of the features and may perform poorly if the scales are very different. So it's normal to scale the features. In these simple vanilla examples we've been looking at, we have already scaled the data. Like in this case, which we had up here, we've actually scaled X to be given by a random number defined by the uniform distribution, which means that the data are set up for X between 0 and 1. So this is a pretty, this data already scaled. Now, I've had cases where we had a student who wasted 2 to 3 months on the master thesis because the weather data which that person got were, depending on the year, were logged either as for the wind speed, either as kilometer per hour or meters per second. And in the beginning, when that student was looking at the data file, there were no indications that different units had been used. And that really caused a lot of problems in the setup of a linear regression algorithm because the data came with different units. And this is something which can be pretty, how to say, irritating when you, especially when you're doing a master thesis and you have a specific deadline for handing in your master thesis. And going through the data set, there were no indications that in different years, the wind speed had been measured in different units. So pre-processing the data is something which is pretty common. So there is a function which is called the min-max scaler, which ensures that all features are exactly between 0 and 1, if that is needed. There is another pre-processing feature, which is called the normalizer. And then there's also the roboscaler. But the standard scaler is pretty common. And the standard scaler is a procedure where you subtract the mean value for each column. So if this xi, which you see here, is a column vector in your feature matrix or design matrix, then j is a specific component. Now j is a column and I is a specific component. You would then subtract the mean value for that specific column, and then you would divide by the standard deviation. You can take that away, the standard deviation, and simply just center or use the standard scaler by subtracting the mean value for each column. By dividing by the standard deviation, you make your quantities dimensionless. So this is also something you can consider when you're scaling your data, whether it's useful to scale them so that they become dimensionless. So the standard scaler is a function which is included in scikit-learn, and you would simply include this by the pre-processing package, where you have functions like min-max scaler, standard scaler, normalizers, and many other ones. And this is an example of a matrix here where we are doing this ourselves, the same thing as the standard scaler is doing. And in this specific case, what we are doing now is we are setting up a random matrix with 10 rows and 5 columns. I'm setting up my design matrix, and I use pandas and a data frame functionality in pandas to simply set up my matrix. So this is my x pandas is now given by the original matrix with a given number of rows and columns where I've just used a normal distribution. And then I display it, I calculate the mean value, I calculate the standard deviation, and then I set up my new design matrix where I've subtracted the mean value. Just keep in mind then that if you are doing a polynomial fit and you keep the intercept, that column will become 0 because the mean value of a column with ones is just 1. So you take 1 minus 1. So that will give you a column with just 0 elements. And then I'm using the same optionality which I would have in the standard scaler. And then I display the difference between what the scikit-learn is doing with standard scaler here, where I now don't calculate the standard deviation. So I leave out, if you go back to this equation, I'm actually putting this quantity in the denominator, the standard deviation, to 1. So with the STD equal false, that is not included in the scaling. And if I run this code here, what you will see then is this is just the original matrix. These are the mean values. And then this is a new matrix, which I now have calculated by subtracting the mean values. And this is a difference between what scikit-learn is doing and what my code has done here for this simple implementation. There are other ways of doing the scaling, so feel free to ask here if things are unclear. There are other ways of doing the scaling, and one of them, and which is a very popular one, is actually this min-max scaling, where you have a maximum value and a minimum value, typical 0 and 1, for instance, if that is relevant. And this is often done in case you have data which vary a lot. And since you are dealing with the matrix operations like matrix inversions, if the data may vary a lot in values, there may be risks of having a loss of numerical precision with the following errors in the matrix inversion here. So there are examples here where I actually calculate these quantities. And again, we have this simple example here where I have a new vanilla set of data. And now I'm using scikit-learn, the functionality in scikit-learn, and I'm performing a standard scaling with this equation here for y, which is now given by an exponential with x to the power of 2. I have reshaped it because I'm now using scikit-learn. So instead of me setting up the design matrix, I'm actually using this polynomial feature here. So I'm now running over a given polynomial feature. I have 50 data points. I set up my x values, and scikit-learn as a library actually wants me to have x defined as a matrix, not as a vector. And y is also defined as a matrix. So this is a matrix of dimensionality n times 1, because I have only one column. So that's my x here. And I use that one to set up my design matrix according to the polynomial degree. So scikit-learn has a function which is called polynomial features, and that is doing exactly the same thing as we discussed here. So where we were setting up the function as we did here. Now scikit-learn is doing the same thing with these polynomial features functions. I just wanted to show you that kind of functionality because you should feel free to use that functionality. Now here I'm now not including the intercept when I'm making the training. Now one thing which I then do is that I perform my fit for the given polynomial degree, and I calculate my test error and my train error. And these are the same functions which I had before. And I simply calculate the mean of the test minus the prediction, and then plot the final results. So if I do that, we will see something like this. So in this particular case, I have done a train test splitting. And the image which you see here is one of the images we want you to reproduce in this exercise number 3. And this exercise number 3 asks you to plot figure 211 in the textbook by Hasty, because we want you to play around a little bit with the relation between test and training. And one of the things you will see is that when you increase the complexity, so we have a third order polynomial, a fourth order polynomial, second order, first order, this is a 0th order polynomial. If we do that, we see that the training will normally get an error which gets smaller and smaller as we increase the complexity, which is expected. Whereas the fitting or the prediction which we make on test data, which was not included in the training, can deviate a lot from the training. This is still going down here, but if I now increase the degree of the polynomial, suppose now we go to a polynomial of degree 10 of this function, which in principle should be exactly reproduced by a polynomial of infinite degree, because it's an exponential. If you Taylor expand the exponential, you should then, depending on obviously the powers here, you should then in principle actually have something which should run from 0 to infinity. And one of the things you will see now is that when you increase the training, you may actually see behaviors like this on the test data. Now, in our case, we have only 50 points, which means that my test set here is actually only 20% of this, which is only 10 points. So if we now increase the number of points, these results will change. And then we get something which looks like this. We have more training points. The model is giving a smaller and smaller mean squared error. But if I now keep increasing the degree of the polynomial to degree 15, we will see something like this. And then we can now let it go to degree 19. So there's going to be a ratio between the number of points. And you see this is slowly increasing. It's always above the training. The training gets better and better as we increase the degree of the polynomial. But then at a certain point, my test data will start to deviate largely. And that is a signal of us overfitting. Like you see here now, it's increasing. If I keep going, suppose I get more and more ambitious, and I want a polynomial of degree 30, I will get something like this. And now you see that the test error is going up. The train error becomes flat. So what you would say then, depending on the data set which you have and the polynomial degree, so this will be the model complexity, the polynomial degree you have here, you will now see that the test error is increasing, and that is going to be a flag for us about overfitting. So when we come to the discussion of the bias variance trade-off, we will see how we can quantify this type of overfitting. But something like this means that now we are making a better and better training, but we'll come to a region of model complexity where the model is too complex. And then we start overfitting when we apply the model to data which has not been included. So this is something I want you to play around a little bit in this exercise number 3. So where you look at the ratio between train and test data, and you also try to scale the data. Like we did here, we use the standard scaler on the training data only. And we also do that on the test data. So that means that what we do now, we subtract the mean values here. We don't do that on the output. So you can decide whether you want to only scale the inputs or you want to scale the inputs and the outputs. There are some discussions when you follow below here, and I want you to read through this because this is something we are going to pick up next week. So this is about the centering, subtracting the mean values, mean mathematically, or what this function in scikit-learn, which is called standard scaler, is doing. So I would like to have you to go through this material here before we discuss it in more detail when we start next week, because you will get an exercise next week where we are going to play around a little bit with scaling of the data, because that becomes a little bit important when we are going to analyze data and we are going to compare data with what libraries do, like scikit-learn, and we are going to compare that with our own codes. So take a look at these expressions here, and then what we are going to do now is rather to look at the mathematical interpretation of ordinary least squares. And I promised to you that we are going to look at the interpretation of the Hessian matrix, but also the interpretation of what a mean squared analysis actually means. So what we have found is that this beta is given by this matrix here. If I then use the fact that this is our best beta value, if I use our best model now, this is our value for y here. Now, this means that what I have when I multiply with x here times beta, it means that I'm having this matrix to be inverted, multiply with x and x transpose. And this is something which, if we define this matrix here, we can actually rewrite this y tilde in terms of this matrix times the original y. Now, this a squared is the same as a, and that defines a projection matrix. That means that the interpretation we can make of our optimal model y is that represents an orthogonal projection of y onto a space which is defined by the column vectors of x. In our case here, the matrix A is a square matrix. If it is a general rectangular matrix, then what we would have then is an oblique projection matrix. You can also study the error, because if you set up the error, then you have I, the identity matrix, minus this matrix A, which we defined here. And this quantity here is actually a projection which is orthogonal to this projection. So that means that the residual errors are then the projections of y onto the orthogonal component of the space defined by the column vectors of x. Now, there's one thing which I wanted to start here, and we will need to go back to this next week as well, because we won't have the time to cover all of it. But I wanted to discuss the singular value decomposition and how this can be used in the analysis of ordinary least squares and other methods. So again, there's a simple test here. If you have an orthogonal or unitary matrix, then you should have a perfect fit. So that's a useful test of your codes. But what I wanted to say a little bit more about now is actually the link with what we are doing now and the singular value decomposition. So let's introduce a new concept towards the end of the lecture. It's not the best thing to do pedagogically, but I wanted to bring this up because this is where we will continue next week. So what we have is a design matrix, which is given by these different column vectors. Now, there's clearly one thing which we haven't mentioned, and what we haven't discussed is actually whether there are dependencies between the different column vectors. So when we perform a polynomial fit, then we are assuming that every column represents a polynomial degree. And these are in principle vectors which will be orthogonal to each other because they would represent a first order polynomial, a second order polynomial, etc., etc. Now, if we are looking at the data like cancer data, then the different features could be something like the radius of the tumor. It could be the area of the tumor, and the area is obviously something which has to be proportional to the radius. Could be the thickness of the tumor, etc., which again could have some relation to the radius. So that means that we have no guarantee that these columns are independent of each other. If that's the case, then the matrix we want to invert is singular. So if we now go back to the expression which we had for the optimal parameters, these parameters beta, they are given by a matrix X transpose times X transpose times Y. Now, if we can invert a matrix, if this matrix which you see here is invertible, then there is no problem. However, as I said, one of the big problems which we face is actually that there may be dependencies between the different column vectors. Now, from a numerical point of view, what people did back in the 50s and 60s, and also in the 70s, was simply to add, when the matrix was not invertible, or to guarantee that accidental matrix elements could become zero, one would simply add a constant along the diagonal. So the standard trick which was used was simply to add a constant multiplied with a diagonal. So this matrix here has a dimensionality P times P, and that means that this matrix has also to have a dimensionality P times P. And this identity matrix is just ones along the diagonal and zeros else. And then we would simply add a small parameter lambda. So this kind of cheating, as far as the matrix X transpose times X has positive eigenvalues, this kind of cheating would then guarantee that we would get a matrix which could be inverted. Now, clearly, this is cheating, obviously. It was a kind of cheap trick which was used in order to prevent a matrix to be non-invertible. So that would lead to a problem which looks like this. Plus a lambda times the identity matrix, and then we would invert it, X transpose times Y. So next week, we're actually going to meet this in terms of ridge regression. So we can justify this mathematically by optimizing another objective function. And the objective function which we would optimize then would be this one. So it would still have the mean value, 1 divided by n, the mean squared error, I equals 0 to n minus 1, of y of I minus yi tilde squared. But now there is a parameter lambda, and then I sum over all the features, which I have p minus 1, and I have a beta j squared. If I take the derivative of this function with respect to the parameters beta, then I will get, and we will show that next week, I will get this function here. And that is a very important result. And because then we can start mathematically with another objective function we want to optimize, but that will include a new parameter, which we call a hyperparameter. And we can tune that parameter so that we can get a better mean squared error than we would get with ordinary least squares. The other thing which we are going to do now, next week, so the material you find today is also material we will use next week, is to introduce a singular value decomposition. So what does that mean? That means that the matrix X, which we have, can be decomposed in an orthogonal matrix U. So any matrix, even if the matrix is singular, can be singular value decomposed. So SVD stands for singular value decomposition. That can be decomposed into three matrices, where U and V are orthogonal or unitary matrices, and sigma contains what are called the singular values. So let me just set up this, and then we are done for today. And this is where we will start next week. So X can be a matrix of dimensionality n times p. U is a matrix of dimensionality n times n, and it is a unitary or orthogonal matrix, which means that if I do this, for an orthogonal matrix, I get the identity matrix. V is also an orthogonal matrix, but it has dimensionality p times p, and V times V is equal to V times V of t, and that's also given by the unit matrix. This is actually a fantastic theorem in linear algebra. So if you haven't seen that in a linear algebra course, please take a look at it. It's normally taught with many of the linear algebra algorithms. And sigma is a matrix of dimensionality n times p, and it is a matrix which contains the singular values. So it will contain a sigma 0, sigma 1 to sigma p minus 1, and then it will have zeros for the rest. So this sigma 0 is larger than sigma 1, so this is just one hierarchy you can opt for, and it's larger than sigma p minus 1, which is larger than 0. So these are called the singular values. And this is where we will start next week. It's always not the best thing to start with a new concept at the end of a lecture, but I wanted just to bring up what is going to come. So we are going to make a singular value analysis of the ordinary least squares, but we will also apply that to ridge regression, And we are going to study ridge regression and another type of regression, which is called lasso regression, in more detail next week. So that's the topic for next week. Now for this week, if you have time, please feel free to look at the exercises from last week. And next week, you will get new exercises which deal more with implementing lasso and ridge regression and compare that with the ordinary least squares. And this is where we will stop today.